Up to this point, we have learned how to solve one-dimensional problems with kinematics. Our goal now is to learn how to solve two-dimensional problems with kinematics. Two-dimensional problems have the added complexity that vectors like velocity point at angles, like a baseball thrown through the air. So here's a baseball with a velocity immediately after being thrown, and as it travels through the air, it might follow this path. So a moment later, it might wind up here with this velocity. And then another moment later, it might be here with this velocity. So the point being that the velocity vector keeps changing. So how do we deal with this? The answer is that we will do just what we did before with 1D kinematics problems, but now we must know how to do the associated math with vectors. In this video, we'll discuss the basics of how to write down and draw vectors, and then in the next video, we'll discuss how to do math with them. To begin with, we typically put an arrow or partial arrow over the top of it to indicate that it is a vector. As examples, here are 4 vectors: velocity, acceleration, displacement, and force. In textbooks, you may see these vector symbols bolded rather than having arrows above them like this. Remember that vectors include a magnitude and an angle. Sometimes we need to refer to the magnitude aspect of a vector. So to do that, we put absolute value symbols around the vector like this, or the vectors may be written without the arrow on top and not bolded like this. For clarity, I'll write vectors and the magnitudes of vectors in these forms. We also need to know how to draw vectors. When drawn, a vector should indicate direction and relative magnitude. As an example, let's look at the thrown ball again. Pretty clearly, the direction that these velocity vectors point indicates the direction of the ball's velocity at various instances in time. In addition, the length of each vector indicates the relative magnitude of each velocity or its speed. For instance, we know that the speed of the ball is greatest here because the length of the velocity vector is greatest here. Another thing to point out is that, strictly from a mathematical sense, the location of the vector doesn't matter. For example, here are 2 different balls flying through the air. They're located in different places, but their vectors have the same length and direction, so mathematically, velocity 1 equals velocity 2. Now let's discuss writing vectors numerically. Vectors may be written in Cartesian form or polar form, just like our previous discussion on coordinate systems and plotting locations in them. As an example, here's a force vector. To describe its magnitude and direction, I'll put it on a coordinate grid with the base of the vector at the origin. We then use the coordinates of the tip or head of the vector to describe its magnitude and direction. So the tip of the vector is here. Based on this, the x-coordinate or x-component of this vector is 7 newtons. And then the y-coordinate or y-component is 4 newtons. As a detail, notice that there are no vector arrows over the x and y components. They're just over the actual vector. In some textbooks, the Cartesian form of the vector, also known as the xy form, is just expressed this way, or it may be written with angle brackets like this. This is a form that I'll use often in class. In polar form, we use the magnitude of the vector, which is its length, shown here, and an angle reference to something. In this example, I'll reference it to the positive x-axis like this. And we can do the same basic calculations we did previously when discussing locations on coordinate systems. Basically, we'll make the vector the hypotenuse of a right triangle and then use trigonometry to solve for the magnitude and the angle. So here's the right triangle, which I've redrawn off to the right for clarity. And we can calculate the magnitude of the vector from its x and y components with the Pythagorean theorem, which comes out to be 8.06 newtons. We can find theta with a trig function. I'll use inverse tangent, which comes out to be 29.7 degrees. We now can write the vector in polar form in much the same way we wrote position in polar form on coordinate schemes before. and it comes out to be 8.06 newtons, 29.7 degrees counterclockwise from the positive x-axis. As we did with position coordinates before, we can reference this vector to something else other than the positive x-axis. For example, we can reference it to the positive y-axis in this case, and so we would use this angle, which I'll call phi. As you can see in the picture, phi is 90 minus theta, which is 60.3 degrees, and so the force vector can also be written this way: 8.06 newtons, 60.3 degrees clockwise from the positive y-axis. So that was an introduction to vectors. In the next video, we'll learn how to do some basic math with vectors.